Okay, so the last part of this unit focuses on intermolecular forces, which is abbreviated IMF. I want to make it clear what the difference is between intra and intermolecular forces, because this often becomes a problem for some of the kids. All right, when we're talking about intramolecular forces, intra means within. So for example, if you had a methane molecule, CH4, and you had H singly bonded to C all the way around in a tetrahedral design with a bond angle of 109.5, as we've talked about previously, the intramolecular force here, or forces, are these covalent bonds, of which there are 4. So that's a covalent bond. So a covalent bond is an example of an intramolecular force. That we've already talked about. You now feel comfortable drawing compounds that have single bonds versus drawing those that have multiple bonds, that is double and triple. Remember, you can't have a quad bond. An intermolecular force is a bond between two molecules. So intermolecular force let's say, for example, there are different types which I'll go through. Let's say you have a methane here and a methane here and a methane here, etc. When these methane molecules are close enough together, they will form very weak interactions. That's too big. And these are intermolecular forces, where this is an intramolecular force. So intermolecular forces are between two molecules, okay? We are going to talk about intermolecular forces today, which are abbreviated as IMFs, even though you'd think you could abbreviate that one the same way. You don't. You usually don't say intra, you just say covalent bond. We're going to talk about some different intermolecular forces today. And this all links to everything we've been talking about this unit, where we're trying to have a better understanding of covalent compounds. Before I get into the intermolecular forces that exist between covalent molecules, I just want to mention a couple of key points. The intra versus inter is in your notes already. Where these intermolecular forces become important is when you're trying to understand properties of liquids and solids. You're trying to understand why certain substances melt at low temperatures versus high ones, why certain substances boil at low temperatures versus high ones. So, in B, it has a brief introduction. When you heat a liquid, the particles will move faster, their kinetic energy will increase. When they move fast enough to break these intermolecular attractions, the substance then can undergo a change in state from liquid to gas. The substance will boil. And what we have noticed, for example, is that if we compare boiling points of ionic substances with covalent ones, for example, potassium chloride and sodium chloride are both ionic substances, methane, water, and a hydrocarbon here are covalent substances. First question, how do I recognize quickly an ionic substance as compared with a covalent one?
Covalent is formed between two nonmetals.
Covalent substance, you've got two or more nonmetals, and do they share or transfer electrons? Share. With an ionic substance, you're going to have a metal and a nonmetal, a metallic cation, a nonmetallic anion. And here the electrons are transferred, okay? That's a key point that you want to understand between ionic and covalent. So the ionic substances here, if we compare melting point, what would you say about the melting points of the two ionic substances here versus the covalent ones?
They're relatively more, they're more higher.
They're a lot higher, considerably higher. This is degrees Celsius. These both melt at about 800 degrees Celsius. These surround 0. So a significant difference, okay? Similarly, the boiling points of the ionic ones are much higher as well. And that tells us that if you are melting or boiling, what you are breaking are these intermolecular forces. So ionic substances must have much stronger forces between them than covalent ones do. First point you want to understand. The second piece of the puzzle that we really want to look at here are the intermolecular forces found in covalent compounds. And I'm going to go through this very carefully and not nearly in as much detail as your notes have. There's a lot of information there. You really only need the bare bones at the honors level. I like to mention this in honors for two reasons. The district requires it, and the second reason is I have found that when kids go to college chem or AP chem, they find intermolecular forces to be overwhelming. So I'm hoping this will make it a little bit easier. I'm curious to see how it goes in AP this year. In any event, when you're considering intermolecular forces, again abbreviated as IMFs, for covalent compounds, and again, these will be between covalent substances, there are three types that we want to look at. The first, which is the weakest, are the London dispersion forces. LDFs. These are the weakest of the three we're going to mention, and I'll give you examples of all of them. The second is a dipole to dipole interaction. And we've talked about dipoles already. What's a dipole? Go ahead, Chris. Talked about a little the other day with the partial charges. You had answered that question for me.
Alright. So it's a dipole that has a covalent bond, but it's not an equal bond. So there's.
What do you mean not an equal bond? What's in the bond?
You have two different elements that are bonded covalently, and one of them has higher electronegativity
Okay.
than the other one. So it's gonna, attract the electron a little bit more.
Okay, so what makes up a single covalent bond?
The sharing of electrons.
One shared pair of electrons. And as you said, it's not shared equally, and the more electronegative pulls those electrons toward itself. And as a result, the more electronegative atom has a partial what charge?
It has a partial negative charge.
Exactly, just as we talked about the other day. So now we're going to look at dipole to dipole interactions. You're going to have a dipole and another dipole interacting in some way, and we'll give an example there as well. Good job. And then the third one is a hydrogen bond, and that's the one you probably have heard of, a hydrogen bond. And we'll give examples of all of these as we go.
So the hydrogen bond is the strongest.
Absolutely. In terms of the strength, that's increasing strength as you go down. And then if you had an ionic compound, an interionic interaction would be stronger than all of those. And that's one question off your classwork you'll see right away. All right. So these are the three types of intermolecular forces that we want to talk about. And I'm going to diagram them out very simply, show you a couple little video clips so you can see them in action. The first, which is the weakest, is the LDF, London dispersion force, sometimes called a dispersion force. London is for a person. LDF is the weakest type, and what you're considering here, for example, is let's say you had methane, which, as we discussed the other day, is a nonpolar covalent molecule. And why is this molecule nonpolar covalent?
It's symmetrical on every side.
It is symmetrical, absolutely, and also the bonds here are polar or nonpolar. These are nonpolar bonds. So you have all nonpolar bonds. The molecule is nonpolar, although it does exhibit symmetry. So this is a nonpolar molecule. And if you had another methane, these two molecules can attract one another somewhat. The attraction, though, is very, very weak. And we'll take a look at a London dispersion force two different ways. Now this molecule here does not have dipoles, correct? Because it's nonpolar covalent. What happens with two nonpolar molecules is when they get near one another, they can almost excite one another. And initially you've got these unpolarized molecules with equal distribution of electrons in the bonds. But as they get close to one another, they can induce dipoles in one another, and they can have instantaneous dipoles. They don't last long, and they're only there when the molecules are very close to one another, but an intermolecular force can form. And the only type of intermolecular force that nonpolar covalent molecules can have is a London dispersion force. And that's what we're going to look at here.
In solid carbon dioxide.
The whole thing is cockeyed. Hang on. All right, it's going to start again.
In
Here.
solid carbon dioxide, dry ice, nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
All right, so the only type of intermolecular force found in nonpolar covalent molecules are London dispersion forces. They're the weakest. That's why nonpolar molecules will typically boil and melt at lower temperatures than polar molecules. All right, let's take a look at the next type, which is a dipole to dipole interaction. For example, let's say that you had hydrogen chloride. Hydrogen chloride is a polar molecule. And polar molecules have LDFs as well, but they also have dipole to dipole interactions. And you're going to see this on the next clip, but you find that these molecules align themselves such that the dipoles always point in the same direction. Again, chlorine is more electronegative. It draws the bonding electrons to itself, and there's an interaction between the dipoles, and that is a dipole to dipole interaction. And so if I asked you what type of intermolecular forces can exist between neighboring HCl atoms, you would say dipole to dipole, because the molecule is polar covalent, as well as LDFs, because all covalent molecules, polar and nonpolar, have the weak ones, LDFs. But this is why you typically find that polar covalent molecules boil and melt at higher temperatures than nonpolar covalent molecules. And that's what you will see here. Now they gave you hydrogen fluoride. I didn't on purpose, because hydrogen fluoride exhibits another one that we'll see next.
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole.
Why does this molecule that has polar bonds not have a net dipole, which means it's nonpolar covalent?
Because don't the dipoles cancel each other out?
Why?
Because if you have a negative charge on like one of them, it evens out the charges.
Why? Go ahead, Abby.
They're symmetrical.
Because it's symmetrical. So the dipoles cancel because the molecule exhibits perfect symmetry. You can get perfect symmetry in a linear, trigonal planar, tetrahedral molecule as long as all the atoms are the same or have grossly similar electronegativities. All right? Good job.
For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules such as sulfur dioxide are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
And one thing I just
Bonds
want
between atoms with different another molecule.
at that point, the dipole to dipole interactions you would see right there right there, right there, right there, right there, between molecules. Now we know dipole to dipole interactions are stronger than London dispersion forces. Polar molecules such as sulfur dioxide also has LDFs. What would you guess is stronger, a covalent bond or an intermolecular force such as a dipole to dipole interaction? Katie? Absolutely. Covalent bonds are much stronger. Intermolecular forces have about 1% the strength of a covalent bond. And you can visually see it, and you've used the molecular model kits as well to see just how strong those bonds are. You're not going to just break them, okay? So that's your dipole to dipole. Now, some molecules have special types of dipole to dipole interactions or earning a name of its own. The other type of intermolecular force that covalent compounds, some polar covalent molecules have, thank you, is hydrogen bond. Sam, this is for you. And some will argue that a hydrogen bond is a special type of dipole to dipole interaction. For example, water has the ability to form hydrogen bonds. And you've probably seen hydrogen bonding before with earth science, where you talked about the importance of water, or in biology where you talked about how bases link up to one another, and we'll take a look at that. But if you have water molecules, and let's say you've got a water molecule here as well, this is a special type of interaction in which a hydrogen atom that is covalently linked to an O, N, or F the hydrogen atom that's covalently linked to an O, N, or F can hydrogen bond with another electronegative atom, again, could be an O, N, or F. And a good example would be water, ammonia, hydrogen fluoride. The H has to be covalently linked to an O, N, or F, and that's the key. That's your hydrogen bonding, and let's take a look at hydrogen bonding with water, and this also will help to explain why water expands when it freezes.
Strong intermolecular attractions.
I've got to grab the cursor and let it rip quickly. Ready?
Strong.
No, it's not going to go. All right, here we go.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with 2 hydrogen atoms and 2 unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So why does water expand when you freeze it?
Because it goes from being like loosely floating and stuff to be forming those intertracheal channels, like you said.
Exactly. And that's why water's one of the few that expands when you freeze it. Most liquids contract. That's why you don't put very full water bottles in the freezer, or like my husband, he puts his Diet Coke in the freezer, forgets about it, and the next day it explodes, and then we have a fight. All right. So, of these, hydrogen bonding is the strongest. But again, one thing I really want to make clear to you is that if you have a non-polar covalent molecule, the only type of intermolecular force you can have is what? LDF. If you have a polar covalent molecule, such as sulfur dioxide, like they showed you, you can have LDF and dipole to dipole. And in water, not only do you have LDF dipole to dipole, you also have hydrogen bonding. I think you've got it. All right, I just want to make sure the hydrogen bonding is clear. Question. Of course you can use the bathroom. When you gotta go, you gotta go. Excuse me. All right. So in your notes, I really put a lot of stuff in case you want to read it, but you want to keep it simple.
It says we're only doing covalent molecules. Maybe we're just not there yet, but do we have places with ionic molecules?
The only thing you have with ionic ones are interionic interactions. The only thing that you should know that I didn't ask is that interionic interactions are stronger than the three I just mentioned. And that's why ionic substances boil and melt at higher temperatures than covalent ones. Your notes go into great detail with London dispersion forces, like I said. London dispersion forces are the weakest. The only type of intermolecular force that nonpolar covalent molecules have are LDFs. That's all you need to know. Dipole to dipole we mentioned, and then if you look at this table here, why would carbon monoxide have a higher boiling point than nitrogen gas or oxygen gas? Because it's polar covalent. So not only does it have LDFs, it also has dipole to dipole. And then hydrogen bonding is shown here, as I illustrated for you and you saw. I do want to mention this first example here because sometimes you have to draw it out to really get it. So let's take a look here. In the examples, it says, for each of the following, indicate whether hydrogen bonding through an available H is an important intermolecular force. And the one that you see on the test will probably be one of these. Now, if you only had N2, does that even have a hydrogen to form a hydrogen bond? No, so that one's yucky. If you had hydrogen iodide, can that participate in hydrogen bonding? Is the H bonded to an O, N, or F? No. If you had hydrogen fluoride, how about that one?
Yes.
Yes. Chris, you have a question?
Yeah. Could the hydrogen iodine one, could that form a dipole one?
Absolutely. That'll form dipole to dipole interactions.
What about the nitrogen? Would that just form an LDF?
Correct, because that's nonpolar covalent. This is the one that I thought might be a little tricky, that some of the kids might say, oh yeah, look, the H is attached to the O, but it isn't. And that's why you have to draw it out. This is actually an aldehyde, which a lot of you did draw yesterday correctly on your quiz. But is an H attached to an O, N, or F? No, so that one's a no. And then this one is methanol. Methanol is an alcohol. And when you have alcohols, you have have this OH group. Is this H capable of participating in hydrogen bonding?
Yeah.
Sure it is. So for example, this is an alcohol, and this helps explain why bartenders can water down drinks, because alcohols will link to water via hydrogen bonds, dipole to dipole, LDFs, and that's why alcohols are soluble in water. That's also why you can make 91% isopropanol, 70% isopropanol. That's what you would use. It's probably in your medicine cabinet to clean out cuts and stuff, things like that. Also, if you get your ears pierced, you get some form of, it's usually isopropanol, to make sure you don't get an infection.
What is hydrogen peroxide?
Hydrogen peroxide is also used to clean out wounds. You actually drew this one in the lab the other day. This is also capable of hydrogen bonding, but hydrogen peroxide is also used to disinfect wounds. They actually say this is a lot better to use than rubbing alcohol, because with rubbing alcohol, which is isopropanol, you'll continue to bleed, or you might bleed more, where this does not cause more bleeding. This also works really well to remove blood stains from anything. The last thing I just wanted to mention briefly was to link you back to biology, because I know you guys really enjoy biology, and I'm sure you remember your base pairing. Adenine A bonds with thymine T, remember?
C.
And cytosine C. Ooh, my pointy's gone. Oh well, there it goes. Bonds with guanine, but that bonding or linking, these are actually hydrogen bonds right here. So I have a question. If you wanted to melt a strand, a double-stranded DNA, which would melt at the lower temperature, an A to T or a C to G? Go ahead.
And A to T would melt faster because it has less hydrogen bonds.
You got it. An A to T base pair would melt at a lower temperature because it's only linked via 2 hydrogen bonds. You'll also note that this H is attached to the electronegative N, and it hydrogen bonds with the electronegative O. This H is covalently bonded to the electronegative N, and it hydrogen bonds with the electronegative N, and you see more of it here. And if you've ever watched the movie Race for the Double Helix, which showed James Watson, Francis Crick, Rosalind Franklin, as well as Maurice, I think is it Wilkins or Wilkinson? Wilkins? I can't remember. And I can't remember if it was Watson or Crick that was playing with the bases to get them to link, and I want to think it was Crick. And it's very interesting how he played around with these different base pairs in different forms to see the hydrogen bonding that could occur, because they weren't chemists. All right? So make sure you can differentiate between a polar and a nonpolar molecule so that you can tell whether the molecule exhibits LDFs only, LDFs and dip to dip, as well as all 3. All right? Questions here? Yeah, you can fight over who goes first. I think she really has to go. She's going to go in her pants.